don't think we have a 10-minute rule, so we'll get going. Okay, good morning, everyone. Welcome to CITA seminar. Today we have a talk by Professor Essick, someone who needs very little introduction to our local citizens. As you know, Reed is, of course, one of our very active faculty members, and also is organizing the summer undergraduate research program, and he runs our national mentorship program. And in addition to doing all this fantastic work that we can hear about, I will get out of the way quickly, just give you a very quick bio. Reed obtained his PhD in physics at MIT in 2017. Got his thesis title, which was the detectability of dynamical tidal effects and the detection of gravitational wave transients with LIGO. Reed entered this field of gravitational wave detection before there was any detection, so it was a risky move at that time, which of course turned out to be a very good decision. Reed was involved in the very first detection and ultimately all subsequent ones, but the most famous ones you've heard of would be ones with the first black hole detection, the black hole neutron star. And Reed was right there, perhaps one of the first few people to see them. And we can hear some interesting stories as we talk to him about what he was doing and how the consortium was reacting when these detections happened. After his PhD, Reed went for a postdoc at the Kavli Institute of Cosmological Physics at the University of Chicago. And that then led to his coming to Canada. He took a second postdoc at the Perimeter Institute, and that was in 2021, I believe. And then soon after, late 2022, Reed came here as an assistant professor. It's been 2.5 years, and it's been great to have you here. And we're going to hear about neutron stars and much more. Thanks, Reed.
Thank you, Shantanu, and thanks everyone for coming. Really excited to be able to tell you about so the things I've been thinking about for the past few years and really where I'm excited for the field to go. So as Shantanu mentioned, I started here in 2022, 2 years ago. So I'm going to cover some of the work that I've been doing here, but of course, stretching back a little bit beyond that. So one of the things that I actually like to do, because it's not common that you get to do this in astronomy, is make slides to scale. This is a scale representation of how big a neutron star and a black hole would be if they were each about 1.5 times the mass of our sun, and you can see that they fit conveniently between us and Niagara Falls, and we get to watch these things smash into each other at essentially the speed of light. So I emphasize this because this is very extreme scenarios. This is not run-of-the-mill normal matter. This is really testing our understanding of fundamental behaviors of physics and our theories about what goes on inside these very incredibly dense stars and the very strong gravitational fields around them. I'll also point out that there is this QR code here. If you want to chase any of the links, this will take you to a public version of the slides. It will appear at the end of the talk as well if you want to snap a picture of that. Okay, so I am going to be focusing mostly on neutron stars and black holes and really what multi-messenger observations of these systems can tell us about our theories about the underlying universe. Briefly, here's a rough outline of what we're talking about. So I'll introduce some of the basic observations focusing on gravitational waves. As Shantanu mentioned, I've been working with those for quite some time. We'll then cover the more general observables, so multi-messenger observables, how we can actually study these stars out in the wild. We'll talk about some of their different types of behaviors, in particular some of the wacky stuff that they can do, and really how we can use our understanding of the theory of how these objects can behave to sort of cover the entire possible parameter space, the entire possible theory space of what sort of objects might exist in the universe. That'll help us learn about the equation of state. I'll show you some cutting edge results for what we think is going on inside neutron stars. And then we'll leverage that to talk about some applications before we conclude with the final prospects. One other sort of initial point is you'll see these chiclets throughout the talk. As Shantanu mentioned, I've worked on the LIGO detectors for a lot of time, but I've also published about hot Jupiter tidal systems and many, many other things. And so you'll see a bunch of these call outs. If there's something that looks interesting to you, please do ask me. Folks online, apologies, I can't see the chat, but people in the room, please put up your hand and ask if there's something that seems interesting. Okay, let's dive into it. So one of the main fundamental pillars of my research program is trying to figure out what the heck is a neutron star. And based on the name, you might think it's mostly neutrons, but it turns out that we don't know if that's necessarily true. So this is a nice little cartoon, this onion slice picture of a star. It's from the MUSES collaboration, which is a collaboration of nuclear theorists and experimentalists and astrophysicists that I'm a member of. They put out a review paper just a couple years ago that is trying to highlight the open questions in the field. And so if you go deeper and deeper into this star, as unsurprisingly, you go to higher and higher densities. And what's really unique about neutron stars is if you look at the sort of the outer core and the inner core, the densities that you reach, it may be hard to read in the back of the room, can get up to roughly 10 times nuclear saturation. And you'll hear me say that term, nuclear saturation or nuclear saturation density, a lot. That's the characteristic density scale that make up the nuclei in the atoms in you and me and everything around us. So all of sort of known physics, terrestrial physics, goes from 0 to 1 on this scale. And then these stars let us to go from basically 1 up to maybe even 10. So a significantly larger density range than we have access to anywhere else in the universe. And so unsurprisingly, we really don't even know what the appropriate description of matter is inside the core of these stars. We don't know whether neutrons and protons are the appropriate degrees of freedom. Is it some other bound state of quarks? Is it some just quark soup, often called deconfined quark matter? We don't know what's going on inside there, and we want to study that. We want to figure that out. So that's a core part of my research program. Another way to look at this is in this phase plane, the temperature versus density plane. And you can see there are a bunch of different types of theoretical calculations. You can do experiments, the heavy ion collisions, terrestrial experiments, but you'll notice that there's a big unshaded region that kind of lives over here, primarily at low temperatures and high densities. And there's a little pink call out here for neutron stars. This is where neutron stars live, typically at low temperatures, by which I mean the thermal energy is much, much less than the Fermi energy of the system, so it's basically locked into its quantum mechanical ground state, but also at extremely high densities that I was telling you about. And so there is no other great way that we know of probing this behavior of matter anywhere in the universe. So if you care about the nuclear physics at all, you are naturally driven to care about neutron stars. But at the same time, if you care about the behavior of neutron stars, how these really interesting, exotic things behave in the universe, you need to understand the nuclear physics because that's what's determining their structure. So both these things are really two sides of the same coin, and it's a common theme that you'll see throughout my research, trying to leverage bits of information from one side to help with the other. Okay. So as we've discussed a little bit, I work a lot on gravitational waves. Here's the obligatory slide describing our gravitational wave detector network. It's a global network. So there are 2 detectors in the States. There's Virgo in Italy, Kagra in Japan, where Shantanu just was. LIGO India, I believe they're about to, or they will very soon break ground to have another detector there. And so these are incredibly precise instruments. If you want to know about the detector response, data quality, calibration, I've published on all these things. I love to talk about them. Unfortunately, we don't have too much time to go into them tonight or today. But the magic of these detectors is basically if you have some signal, we'll talk about the physics of this in a second, some gravitational wave signal from, say, a binary containing 2 compact objects, this lets you just directly transduce that gravitational wave signal into something that you can read. And so this plot here that I'm showing is from the first direct detection of gravitational waves, and the data you can see here matching the theoretical prediction pretty well. This is just directly reading off what we call the gravitational wave strain, or like the amplitude of the field directly, the gravitational field. And so this is an incredibly powerful tool that we have now to study these systems, in particular these binaries that are emerging. So let's talk a little bit more about the physics of that. So you can see I have this nice this picture of an inspiring binary, and it's really a triumph of modern theoretical physics that we have these good predictions for what the signal should look like. The basic physics that you need to know is that we have a system that's 2 compact objects. It matters that they're compact because that means they can get really close to each other before they actually touch. So you can put them on a very, very small orbital separation, and then they will orbit each other very, very rapidly. So very short periods, very high frequencies. And as they do that, they will emit gravitational waves. This is a prediction of general relativity. And so those gravitational waves carry away energy and angular momentum that causes the objects to fall towards each other, which makes them orbit even faster by Kepler's laws. That creates more and more radiation, and you get this runaway effect. So you can see that directly in this signal. The oscillatory pattern is the orbit, so the phase here is directly mapping the orbital phase of the system. As you go along in time, the x-axis is time. You can see that the period shortens, the frequency increases. The amplitude also increases as it's getting closer and orbiting faster, it's radiating more energy. Eventually the objects slam into each other, what we call merge, and ring down into a final state. And so this is the basic physics of this compact binary in spiral that we can look for. Of course, there are many different things that could affect the waveform. So the masses of the system, the spins of the system, if the individual objects are spinning, if they're aligned or precessing. This is a particularly cool one. If the spins of the individual objects are not aligned with the orbital angular momentum, the whole orbital plane can tilt, and they can beam towards you and away from you and towards you and away from you. And that will create this amplitude modulation as you get more power beamed towards you, beamed away from you, beamed towards you. So there's a lot of really rich physics that goes on in here. And in fact, again, anything that affects the orbital evolution will be imprinted directly into this gravitational wave phase, and is something that you can test. So that includes alternate theories of gravity, like deviations from GR, what if other, gravity actually behaves slightly differently than GR? And this is something that Yi Wang, who is my master's student for this year, sitting right there, he's working on this summer, is looking at ways that we can use very generic approaches to try to test to see if gravity is correct in these systems. The feature that we're going to look at most for today, though, is the effect of matter in the system, and particularly the effect of tides. And so, as was alluded to in the title of my thesis, I've worked on other types of tidal interactions. We're going to mostly worry about the type of tide, like the moon raising a tide on the Earth, this sort of large-scale deformation in the star. What that does is it changes the structure of the star, right? So it makes it more oblong because you've raised the bulge. That will actually cause the gravitational radiation to be more loud, more pronounced. It will radiate energy more quickly. There's a bigger quadrupole over this. And so because you're losing energy more quickly from the system, the orbit will evolve faster. And if you look very carefully here, you can see that the blue, which is the system that includes the tides, has fewer cycles than the gray, which does not include tides underneath. And so the orbit goes through fewer cycles before it plunges because it's radiating energy more efficiently because the objects are not spheres, they're oblong by these tidal effects. So again, it's the tides that are changing the orbital dynamics in the system that is directly printed into the waveform, and the system can directly basically read off from the data that we collect. So if we care about what neutron stars are doing in these systems, neutron stars are doing their matter. They have this sort of tidal deformation, and we can, again, read it directly from the system. So let's talk a little bit more about other things we can observe with neutron stars, and I'll try to convince you that neutron stars are the original, the best multi-messenger source out there for a bunch of reasons, and hopefully you'll see why it's so fun to work on them, because you get to think about a bunch of different observations. So the first thing that you can ask, you have a neutron star, what are its properties? Well, how much does it weigh? Very simple question. What is its mass? The best way we have to measure this right now is in radio. So messenger 1 is radio. And the basic idea is that some of these radio pulsars are in binaries. And because the radio pulsar is rotating at a very consistent period, you can very carefully track when those pulses are hitting you and use that to map out the entire orbital solution, basically, of the object in this binary. And that gives you a really good estimate of the mass of this particular object. Why does that matter? You'll see this type of plot show up a bunch. On the y-axis, I'm showing the mass of a star. On the x-axis, its radius. Each one of these curves is a different possibility for what fluids could be doing, the equation of state, what we call. And you'll see that they all sort of swoop up, but there's a lot of different behavior. There are zigs and zags and kinks and wiggles. However, for each curve, there is a maximum. That's called the TOV limit, the Tolmanov-Volkov limit, and the fact that for each equation of state, there is a maximum mass that can be supported is a very generic prediction from general relativity. And so if we see an object that we're confident is a neutron star, and we know its mass, then we can be very confident that these curves, whatever describes the true equation of state, must go into that region. It sets a lower bound on the mass. So just observing pulsar masses already gives you a lot of information. You know your curve has to go up into this region, so these ones are disfavored, and these guys are okay. So messenger 1, radio, gives us mass. Messenger 2, X-ray. So we're still talking about electromagnetics, but very different part of the spectrum. Recently, the NICER telescope, which is a calorimeter that's about the size of a washing machine bolted to the ISS, It is a very good calorimeter in that it measures the energy and the time of arrival of X-ray photons exceptionally well. And so if you stare at an X-ray pulsar, this is again a neutron star that's emitting X-rays, you can count both the energy and when those photons hit your detector very, very precisely. What that means is that you can try to map out, as a part of the rotational phase of the star, when most of the photons are being emitted, or generally how that flows. The physical picture that we have in our head is that there's a thermally hot spot, like a toaster, but so hot that it's emitting X-rays, just thermally, on the surface of the star. And by modeling both the temperature, the location, the shape of that object, and the mass and the radius, the full space-time surrounding the object, you can make a prediction for what this phase, this X-ray phase profile should look like. And that lets you compare the data and then get a measurement of the mass and radius. So this will look like this, these blue blobs on the mass radius diagram. And again, the cartoonish picture is you want the lines to go through those blobs, and then they're good. And so we can have one messenger from X-ray, another messenger from radio, combine the information. Unsurprisingly, we have more messengers. So gravitational waves we've already talked about. And as I mentioned previously, there are many different types of tidal effects. I've worked on some of them, including secular tidal effects. The main one that we have observed, that we have good evidence for so far with actual observations, is this quasi-static or adiabatic tidal deformability. This is a large-scale deformation in the star. Again, much like how the moon raises the tide of the First Ocean, that's the type of physics that changes the orbital evolution, directly imprints on the waveform and something. And so, as you can see, we have 1, 2, 3 messengers. Neutron stars are the original, the best multi-messenger source. This is some examples of how you can use different observations to probe the same underlying physics, because they're all related to neutron stars. We also occasionally get to see bright flashes in the sky when the neutron stars themselves explode, and you can observe multiple messengers from the same individual source. But that is actually a narrow definition of what it means to do multi-messenger astrophysics. These observations could be of completely different stars in the sky, but because we believe they all obey the same underlying physics, we can nevertheless use those multi-messenger observations to learn about them. And I truly believe that that is the direction that the field that we're going to profit from moving forward, is this idea of using all information regardless of what the source is, to try to learn as much rather than waiting for individual golden events that have all the messengers all at once. Okay, I'll skip this for any detailed description, but basically we have this tidal deformability, we have the mass, and again, you'll have some measurement uncertainty blobs you're looking for the lines to go through. Plotting tidal deformability separately from radius, because they are actually two separate independent properties of a neutron star. They're closely related, but they do give you complementary information. So let's now talk a little bit about the exotic behavior that these compact objects can have. And so what I'm going to try to drive home is, there's a lot of things that we can observe about neutron stars, but without a good theoretical prediction of what type of behavior is reasonable or even allowed by our understanding of the laws of physics, you're kind of adrift. And so I'll show you how we can use our understanding of theory to sort of put bounds on what type of stuff we should look for. Just to put some numbers in the back of your head, in case you don't think about this every day, if you look at the equation of state, so zero temperature, as I mentioned for these systems, very low temperature, the equation of state is basically a relationship between the pressure and the density. On this plot, I've annotated nuclear saturation density, 2 times saturation, 3, 4, off you go. And I've also called out in these black dots what the central density would be of different mass stars. And so you can see even a solar mass neutron star would already have a central density that's twice nuclear saturation, twice as big as anything else that we can probe terrestrially. A 1.4, sort of a canonical, lives between 2 and 3. 2 solar mass neutron stars almost way up at 4. And for this particular equation of state, the maximum mass is at almost 6 times nuclear saturation. So again, these are much higher densities than we're able to probe, and sort of the meat of the neutron stars that you might think are going to be somewhere between like 2 and 4 times nuclear saturation. And radii are typically around 12, maximum mass is around 2. Those numbers will also show up a lot. Okay, so this is a plot from a recent publication. This was an AppJL that I put out last year. And so what I'm showing here is, again, mass versus radius, mass versus tidal deformability, but then also central pressure of the object. And each color here is a different possible equation of state. And so the point of this paper was try to explore the different types of behavior that are possible, and in particular, how you can be sure that you've captured all of the physically interesting behavior. And so, as you can see, sometimes the masqueraders curves can be pretty smooth. Sometimes, though, they can have sharp kinks in them, or as Alicia, who I don't know if she's here, called this when we came across something similar in a mini course I taught, a bird's beak feature, because this actually like hooks down, it's very pointy. So you can get a lot of interesting behavior here. And so the question is, which of it do you care about? And how can you be certain that you've caught everything that you care about? And so the definition of stuff that I will care about right now is that the star needs to be stable, by which I mean it needs to be dynamically stable. If you came up and kicked the star, it should sort of oscillate rather than like explode or collapse or dramatically change its configuration. Through a lot of work in the 60s and earlier, you can actually diagnose stability in these plots basically by inspection. And so in this plane, you can look at whether the star is stable or unstable, essentially by counting the number of extrema here. And this corresponds to the eigenmodes, the normal modes of the star, like a bell ringing. If you hit a star and it rung at certain ways, these are modes changing stability from being stable, oscillating, to running away and not returning to the equilibrium position. And so you can get this interesting behavior where, for example, the fundamental mode loses stability. At even higher central pressures, it can actually regain stability, and then it can lose stability again. So this could mean there are things like certain masses that have multiple radii associated with them. You have multiple stable stars that could live on these different branches. And if this can happen once, you could ask, can it happen again? How many times can it happen? When can I be certain that it won't happen anymore? Because I care about catching all of these different possible stable islands on these curves. And so before my work, that was sort of a guess and check type of proposition. People would just go up to some high pressure and say, probably got it all, that's fine. And what I was able to show is actually, while you can't trust this n equals 0 as a good stopping criteria, it turns out you can stop at n equals 1. So you have to go a little bit further, but you can be pretty confident once this mode goes unstable, you're done. You're never going to see any more stable behavior. There are some caveats, but not for physically plausible equations of state. And so what this means is that we now have a robust stopping criteria where we can be confident we've captured all of the physically allowed stable behavior of these stars, and then we can go off and do like a systematic search to see what sort of wacky stuff we can find based on knowing that we now can stop what we caught everything. So that led me to discover hippos. I bet you didn't think that there would be a biology connection here. But high pressure objects, I had never seen these published before in the literature, but for my work, and so I get to name them, and they are hippos. The phenomenology is in the equation state, so pressure versus density. If you have a zig and a zag like these types of curves, what this is showing is typically called the first order phase transition, but basically a new particle species starts appearing inside your star. And so because this is a degenerate fluid, if you start making a heavy new particle, the pressure that that particle will contribute is directly related to its number density, which will be low. So it will only add a little bit of pressure, but it could add a lot of density, mass density. And so you can jump this way in density without going much up in pressure, but then at some point you might have made enough of this stuff where it contributes a lot of pressure and the overall pressure will grow again. So relatively high density phase transition like this, which is not physically implausible at all, there are models that absolutely would have particles with roughly the correct mass to appear at this point, can lead to these very long unstable branches that nevertheless do restabilize down here. And so just to put numbers in your head, what I was talking about was neutron stars that have radii around 12 kilometers, masses somewhere between 1 and 2 times the mass of the sun. Some of these objects can have masses less than half the mass of our sun and radii of around 5 kilometers. These are incredibly tiny objects. These would be extremely weird if we saw them. We haven't seen anything like it. And there's some interesting possible observational consequences. The real thing that makes these new is that the central densities of some of these stars would be extremely high, and the pressures would also be extremely high, possibly overlap with perturbative quantum chromodynamic calculations directly. And so previously, before my work, people thought this was way too high. Like we'd never observed anything like it. There was no chance. It's only of theoretical interest, but not really going to affect much in the real world. We were just talking about at Archive Coffee, how people have tried to take these calculations and propagate them backwards, and they have very little constraining power on things that we could observe. However, if hippos exist, they could directly probe this, and this would be a new way to study the behavior of matter at densities that we didn't think could exist. And so this realization, again, is really driven by an understanding of the physics of how these fluids work. And so theory is really, kind of pushing us forward and knowing the types of things that we could study. Very cool. So I'm now going to tell you a little bit about using this understanding of the theory of what types of behavior is possible, how we can then go out and use these different observables, these multi-messenger observables, to learn about the actual equation of state. And so I'm not going to dwell on this too much, but it is a very important part of what I do. Understanding the statistical analysis of data is very important when you're trying to compare your theory to that data. And in particular, I use a tool called hierarchical Bayesian inference every day. It's extremely powerful, and it's very, very well suited to this multi-messenger problem. And so the idea is if you have multiple different events, each one of these, this could be a radio pulsar, this could be an X-ray pulsar, this could be a gravitational wave merger that you've observed. These could be very different systems, but nonetheless, if they're all governed, you believe, by the same underlying physics, your theory about what's going on in the world, you can use all these disparate observations to connect back and constrain this upper level in the hierarchy. There are more technical details, including, you actually observe the data. You have to worry about whether or not you would even detect that system to begin with. This last bit is something that I do a lot for the LIGO-Virgo-Power collaboration. In fact, I don't think it's too much of an exaggeration, if any exaggeration at all, to say that my work in measuring the selection effects for gravitational waves really underpins a significant fraction of the worldwide community for gravitational wave population analysis. And this includes both curating public data products and understanding the theory of how this selection works and what we can say about it. So this statistical machinery is running in the background. It is something that is very important and powerful. You need to include the selection effects to do it correctly, and this is one of the reasons why I work and try to make these selection effect measurements as publicly accessible as possible. But let's talk a little bit more about the physics of neutron stars instead of just the statistics of how we measure them. And so I'm going to show this panel, which will take a minute to get through, but this is current constraints on the pressure and density of neutron star fluid. And so over here, I'm showing what we call parametric analysis. We'll get to this in a second. What I mean by parametric is if you do the simplest thing, you say, I'm going to try to constrain some line on this plot, some function. You might write down some function in terms of a few parameters and then say, great, I'm going to go try to learn what those parameters are with measurements. Now that is an extremely well-principled, I'm not trying to say that that's a bad idea. It's a very, very good idea when you have a good physical theory. However, as I've tried to stress, we don't know what's going on inside these stars. We have some idea in the cores, but we don't even know necessarily whether it's neutrons that are rattling around in there anymore, or is it deconfined quarks, or what's going on. And so instead of trying to span that whole theory space, what people have typically done is just written down a function that they picked out of a hat, and then try to do the inference with that. So that can lead you into trouble. Let me explain. Here's one particular example. If you start with some base level uncertainty, which is this light shaded region, and then you ask the question, what if I had a hypothetical measurement that measured the pressure really precisely at one density? We've picked 2 times nuclear saturation here. So what if you pinch down right here? How does that local measurement affect your uncertainty at all other density scales? And what you can see is that pinching here in this parametric model affects your belief about the pressure at very, very different density scales. It broadcasts this information everywhere. And so again, this is extremely powerful if you have a good theory. Like if you measure the mass of an electron, then you can believe that you know the mass of the electron in other situations. This is not based on such a theory, and so this can lead to what we would call the model misspecification, modeling bias, or a bunch of words discussing it. You'll get the answer wrong. So wouldn't it be great if that didn't happen? Well, thanks to technology that I developed, starting with the postdoc, but the healthy literature that I'm leading at this point, we have an approach. It relies on Gaussian processes under the hood, but if you were applying for a grant, you would call this physics-informed machine learning. And so what it does is it lets you apply a local pressure measurement here, and you can see it affects your uncertainty locally, but not globally. Like it's not changing your beliefs at very, very different density scales. So what this means is that you can be confident that if you think that you're seeing something here, it's driven by data that was measured at that pressure. So it gets away from this sort of broadcasting theoretical prior issue pretty cleanly. What's even better about it, and this is what really gets me excited, is that the way that it's ballooning, the uncertainty is ballooning here, that's not arbitrary. That's driven by basic physical principles. So we can build into the algorithm how we believe these fluids work. And in particular, we think that the pressure has to increase as a function of density for the fluid to be stable. We also think that the pressure cannot increase too quickly. That's related to the sound speed of the fluid. We think that has to be less than the speed of light due to special relativity. And so what that means is that there's actually bounds on how this uncertainty region can balloon out and be consistent with our understanding of theoretical physics. And so we're able to build this directly into the inference machinery so that every single proposal that we make, we know is guaranteed to at least have some modicum of physical reasonableness. And so this approach that I've pioneered and really pushed forward over the last 7-ish years has solved a lot of these issues in the field, and many, many more people are now adopting this approach for this reason. Okay. So I will also skip this, but suffice it to say that if you put in different possibles, equation of states, and do simulation campaigns, so that's the different rows here, you learn the truth, the black lines, at all mass scales, which is different columns, simultaneously as you get more and more data. So this is a way to argue that our inference will actually recover reliably the true equation of state, regardless of what it is, if you give it enough data. That is simply not true of many parametric models. They would have biases in them. You'd have to worry about that. So we completely get around that. Here are the actual interesting physical constraints. Again, these are with current astrophysical observations. And there are nice stories that you can tell either in pressure or density or mass and radius about where the different messengers are pushing on your constraints. So messenger 1, radio masses, they tend to mean that your pressure has to get really high at some point to support this really, really massive star that you saw. So they tend to push you up here. The gravitational wave observations tend to prefer relatively small tidal deformabilities. That means a relatively compact star, which then means relatively low pressure because the star is sort of crushing in under its own gravity. Those are at sort of the middling densities for more moderate mass stars. And there's a lower bound on the radius from the X-ray observations, which pushes up. And so you have this multi-messenger picture pushing in these different directions. We get to use all this information. Great. The other way I like to look at this, it really just highlights the multi-messenger aspect, is this corner plot, and you're not meant to be able to read these axes, but I'll call them out. This is the maximum mass of a star, the TOV limit. These are radii, these are tidal deformability, and these are pressures at characteristic densities. And if you pick just one messenger, right, just one at a time, gravitational waves are cool enough, right? So we'll just look here. You would get this little pocket, and that's what you get measure. But by combining the different messengers in this way, you not only get the full diagonal, you get off-diagonal terms as well. So you can directly study how knowledge about the maximum mass of a neutron star would affect your knowledge about the nuclear physics governing the pressure directly. And so this big purple box is really the power of this multi-messenger approach to constrain the theory and how it impacts all these other things. And so again, we'll talk a little bit more about applications, but if you do one measurement here through this approach, you can then figure out how the star would behave in other situations. And we'll talk about even more diverse applications of this knowledge than just figuring out what the radius of a new star is. So I've been talking about these sort of theory, like there is definitely strong physical principles built into the inferences, but there are more specific nuclear theories that you might want to test. And so I'm going to talk a little bit about that and how we can connect more tightly with the nuclear theory community and terrestrial experiments. The theory I'm going to pick on is called chiral effective field theory. Super cool for many reasons. It's an effective theory of neutrons and protons and pions rattling around in some bulk nuclear fluid. And so it gives you a prediction for what the pressure is as a function of density. Also, it is able to give you a calibrated ab initio prediction for how uncertain that prediction is based on a truncation error in the effective theory expansion. Super cool. I keep saying this word effective. It means it's not a true theory. It's just an effective interaction that you expect to break down at some point. So if you go to high enough interaction energies, you expect the theory to maybe not do a good job. It's miss some part of your theory, of the important theory. The interesting thing is we don't know what that breakdown scale is from first principles. We don't. So there could be a new particle appearing like we talked about with the hippos. There could be something else that the theory doesn't know about. It could break down at some point. And so there's a natural question, like how can you test that? Can you test it with astrophysical data? And I'll show you, yes, we can. And we can extract meaningful physical quantities without having to bake them into the beginning of the analysis. And so we do this by building self-consistent models that span all densities, trust the theory at very low densities, and then transition to this very agnostic, but still limited by physical principles model at higher densities to test all possible behavior. You can do this where you stop trusting the theory at low densities, stop trusting it at high densities, and then compare what happens in these two cases to learn something about whether the theory in this middle region is a good or a bad description of stars, real stars. Right. So we do this, we construct this set of nested priors, and then you apply the astrophysical observations to it. You get these posteriors, you can see your messengers pushing in the same directions. From a million miles away, these all look right on top of each other, and you see that's great. But if you stare at it for even a second, you'll see that there are differences, particularly down here, and that's where the interesting physics lies. So we're going to dig into that. Just to make sure that we're not picking up something that magically had to be the case, we're going to both consider the real theoretical predictions. We're also going to consider two alternate theories, which have a dramatic softening. So this is, again, like a phase transition, like the appearance of a new particle, causes the pressure to jog over without increasing very much. So this would be some sort of phenomenology associated with a new particle appearing, or a dramatic stiffening. This could be, you could imagine, a hardcore interaction in the effective potential, or very, very repulsive many-body interactions in the fluid. As you crush these particles closer and closer together, it's more likely that you'll have effectively 3 particles interacting than just 2, and so you can have strong repulsive current terms that only matter at very high densities. And so these two theories differ from the true theory at high density. I've constructed them such that they do not differ at low densities, and there's a characteristic scale where they start differing in these units. That's 1 around nuclear saturation. And so what we'd hope to be able to do is tell them apart, tell the colors apart, if we trust them up to high densities, and hopefully then pick out this density scale where they start differing. That's where we would know new physics is appearing or something is breaking down. Lo and behold, yes, we can do this. This is, and I want to stress, this is not some hypothetical 15 years in the future with a super new detector that's not funded yet. This is existing data that has been around, well, since after my PhD began. But for a couple of years now, this is data that's in the can with current observations. It's only going to get better past this. But already we can see that if we stop trust, this is the density where you stop trusting theory. We stop trusting it at low densities, everything matches. That's because we made the theories agree. If you trust them up to high densities, you can tell them apart. This is basically a goodness of fit measure on the y-axis. And so you can see that the yellow is much, much worse than the gray. And if you look at the density scale where they start differing, it is around 1. And so you can then automatically pick out the physical scale where the theories start to differ, where there's some underlying change in the interactions describing actual matter. And so I didn't have to build in any sort of prior assumption that there is a difference. I'm really just looking for when the theory is a good match and when it isn't, but then connecting it to higher density things that I also know are physically plausible. And so this lets me quote unquote discover new physics, the density scale where new physics would be appearing, or at least my theory is breaking down automatically for free without having to sit down and enumerate every single possible theoretical possibility separately. We can do it all at once. You can also then just say, what if I don't know it breaks down at all? And what if you can marginalize over this breakdown scale? And so what that means is you would use the information where the theory seems to be doing a good job and automatically discard it where it does a bad job. So here you would use the yellow information here and then downweigh the heavier stuff because that looks like it's a worse and worse fit. When you do that marginalization, the numbers that you get for the maximum mass are around 2.2. For the neutron star radius is around 12.5. Those numbers hopefully sound familiar to you because when you just consider the astrophysical information, you get numbers that are around 2.2 for the maximum mass and around 12.5 for the radius. And so what this is telling you is that when you include this low density nuclear theory, you are getting a consistent picture with when you just look at the astrophysics. This is primarily because the astrophysics is very, very important in doing these measurements, and they're driving them to some extent. But before my work, where we have this very flexible model that actually lets you be confident you're not extrapolating some sort of local measurement to all density scales, disentangling the fact and showing the fact that some nuclear theory assumptions were not monkeying around with your astrophysics is very difficult. So technology that I developed really helped clarify this statement. So a little bit of math. I promise these are going to be like the most equations that I show in this talk. In addition to just saying good or bad for the theory, it would be great to say like what part of the theory is doing a good job, what part of the theory is doing a bad job. And at least at low densities, we have an idea of what the fluid is made of. We think it's neutrons, protons, and electrons primarily. And so you can write down a pretty simple description of the fluid in terms of the nuclear interaction energy. So this is basically the amount of energy that's in just the interactions in these particles as they're rattling around this fluid. There are many different ways to write this down, but typically you can write it down in terms of the proton fraction, which you don't necessarily know. Things like the energy of symmetric nuclear matter. This is when there are equal numbers of protons and neutrons. The properties of relativistic electron gases, that's what these green boxes are. And then in particular, the red here, this is the astrophysical inputs. You take the energy density of beta equilibrated neutron star matter. That is what you would find in a neutron star. And so if the astrophysics spots in here, based on the colors, you have different terrestrial measurements or theoretical constraints. And there's one free parameter here. This quantity that's called the symmetry energy is the energy associated with taking a neutron, or it's taking a proton and turning it into a neutron in this relativistic fluid. So that costs some energy to do that exchange. This quantifies how much that is. Nuclear theorists and experimentalists are very interested in both what that number is and its derivatives with density. So with this system of equations, you can take any one of our proposals, or equation of state proposals, plug it in here, and then through this understanding of what fluid is actually doing in theory, pick out the symmetry energy, pick out its derivatives automatically. That lets you take the astrophysical constraints that we have from other measurements, masses, radii, tidal deformability, and put them in this symmetry energy space, slope parameter, compressibility. Astro only is the green region. Ab initio theory is the blue, and this little white trapezoid here is terrestrial experiments. Unsurprisingly, terrestrial experiments are the best at this density range because that's what they can probe directly. That's, again, the nuclear saturation is the characteristic density of nuclei that we have access to. So we can see that the astrophysics doesn't really help us that much at these low densities, but nonetheless, we can directly check to see whether the inference from astrophysical behavior is consistent with what we're seeing at low densities, and again, it is. But you can then ask the question, well, what if you had better and better nuclear physics, terrestrial measurements? That's what the different rows here are showing. And so this is the current uncertainty in the neutron skin. This is the property of a lead-208 isotope. People can measure that here. If you improve that uncertainty by a factor of 2, so wave a magic wand and do the experiment for 4 times as long, or you have a really big magic wand and you do a perfect measurement, you can then ask how improved knowledge about the behavior of matter around nuclear saturation affects your knowledge about neutron stars. And so focus on this plot here. I'm showing the uncertainty in the radius of a 1.4 kilometer or 1.4 solar mass neutron star. The green is the astro only. The red is when you have a perfect measurement from nuclear physics. And you can see that the distributions are very, very similar. And so what this is telling you is that even if you did a perfect experiment terrestrially, you knew this number very, very well, there's still a lot of freedom in what the radius of the star could actually be. And I point this out to drive home that it's going to continue to be the astrophysics, are both the theoretical and observational capabilities that will drive forward the field here. It's not like we just need to fund CERN to do a particular experiment. That's not going to get us where we need to go. We need astrophysics for this. One of the really cool parts about working in an astrophysics institute is there are these very concrete things where it's clear that there's no other better way to do it than what we're doing. Okay. So in the last 10 or so minutes, I'm going to flip through some applications. We've learned about the types of exotic behavior these stars can do. We've then learned about the types of actual constraints we can place with current data and what we've learned in different inference techniques to do that. We'll then see how we can take that information and broadcast it forward to different scenarios, some of which hopefully you haven't thought about before. And you'll see how this interesting physics can imprint basically across all of that physics. So the first one that I'll talk about is what's called the lower mass gap. This is primarily an observationally driven feature in the number density of compact objects we see in the world. This is a bit of a cartoon. The actual gap seems to be between roughly 3 and 5 times the mass of our sun, where we just don't see many objects with that mass, many compact objects with that mass. It was originally discovered in observations of accreting binary systems, but it seems to be pretty robust. The actual shape and the roll-off and the position of these edges of this gap, still pretty uncertain, but the fact that there is a gap seems to be pretty robust. And so I mentioned that this gap probably lives and it turns off somewhere between 2 and 3. If you look at the maximum mass of neutron stars, as I mentioned, our best guess is around 2.2 right now. it seems to be a consistent mass scale. And so there's a natural assumption that you want to make, or a leap of faith, that maybe it is this nuclear physics that is determining the shape of this part of the mass spectrum. It's carving out this feature that we see in just the masses of these objects. It could be other formation scenarios, so it doesn't have to be the equation of state, but you can very easily imagine that the nuclear physics could be very important in discerning what this type of feature could do. And so, this is work that I did together with incoming CITA fellow Amanda Farah. She's been really pushing the model for a while, but also Utkarsh Mali, who's been working on it for the LIGO collaboration and used it in his recent short author work, trying to look at just the gravitational wave data alone with a mass model, a mass distribution that has the ability to have some sort of dip here. And so the two parameters you need to worry about in this model, the depth of the dip is called A. Big A means big dip. So very few stars there, and the placement of the dip is called gamma low. Okay, so that's where the roll-up happens. This is with current data, 03 data. The next catalog is going to be released like in October or August or something, very, very soon, and it's going to roughly double the size of our catalog, so we're going to have a lot better results pretty soon. But we can see that the data prefers a relatively deep gap. It doesn't have to be empty, but it's consistent, at least previously, with being relatively empty. And the roll-off tends to be consistent, again, with between 2 and 3 times the mass of our sun, which is consistent, again, still with this maximum mass. So although this gap, this feature, was first detected in other electromagnetic observations, it does seem to be showing up in the gravitational wave observations as well. And this, again, highlights the multi-messenger aspect of this endeavor. You really want to pull together different types of information as much as you can. Another thing that you might ask is, okay, given that there's some gap here, right, how does this affect our knowledge about individual sources? There's a beautiful example of this. This is the event that's been published by LIGO Virgo Kagra so far from 04, 230529, or you might know it as the mass gap event. And so the reason it's called that is because if you do a relatively naive analysis, where you assume that the mass distribution of these stars is flat, like honest to God flat. There's no features, it's just featureless and flat. And then you compare with the data, you infer that the mass likes to live somewhere, the primary mass likes to live somewhere around 3.5 or 4. That's the mass of the sun, which seems to be smack dab in the middle of this gap I was talking about. And so everyone said, oh my gosh, we found something in the gap, it's not completely empty. 2 points I want to stress. We never said it was completely empty. Okay? And in fact, including this event does not change this belief about the shape of the population very much at all. It's consistent with our other observations, very much so. But the other thing is that this assumption about the mass distribution is very naive. We know that there is probably some sort of dip there. And so if you include that information, your belief about the mass of this event go from here to this solid blue, shift to much, much lower, well, significantly lower values. And in particular, if you compare that to the maximum mass of neutron stars, this is my other work, predicting where that lives, then you can see that you go from something being roughly 3% consistent with a neutron star to almost 30% consistent with a neutron star, which I would argue is a qualitatively different statement about your degree of belief of what this object was. So even simple questions like, I saw something go boom in the universe, what was it? They depend on your knowledge of nuclear physics. They depend on your knowledge of the mass distribution. You need to get all these things right to answer this question. And so studying these sort of population assumptions and how they can affect these classifications is what Utkarsh is working on right now to see if we can come up with a systematic picture of what this is doing, so we can have a good roadmap for what type of statements we should be making moving forward. Cool. We're going to stay with Utkarsh's work. So the other cool thing that you can do with these type of features, you can see this is the mass distribution here. I'm plotting the mass this way, the number density down here, is if you have these sharp edges in the mass distribution for how these objects are built, again, that could be driven by nuclear physics or other formation properties. It turns out that cosmological redshift will smear out the position of these edges in the masses that you actually observe in your detector, and it will introduce a correlation with the distance to the object. So larger distances to the object will have higher redshifts, and it makes the masses appear as if they're bigger when we actually record them in our detector, because the waves are getting stretched out physically as a reason. So if you look for a correlation in this detected mass versus redshift plane, the shape of this bending shape is directly a probe of the Hubble constant. And so here you can say, I'm just going to use nuclear physics that I know about. I'm going to use the shape of the mass distribution that I've learned something about as a tool to then go off and do something that, otherwise you might think is completely unrelated. This is called spectral siren cosmology. And so what Utkarsh showed in his paper, just published this year, is that the current constraints from this approach are still pretty weak because the catalog is only modest. However, very importantly, if you have multiple features, those act as independent probes of H0. And so you can beat down on systematics by combining information from multiple of these probes, just like, this is actually very relevant for a paper we're talking in arXiv this morning, if you have multiple lines in absorption spectrum or something like that, seeing them all get redshifted would help you beat down on theoretical uncertainty about any individual line or speaking. And so this is a very cool technique, and Utkarsh was able to show that there's good robustness here moving forward. Okay. So in my last few minutes, I'm just going to tell you where I think the field is going to be really exciting over the next few years. And hopefully I've already gotten you excited about the theoretical, interesting behavior of these objects, what we've already learned, and then some of the applications. I like to use this plot. So this is the mass of the object versus its central density. The way you read this is pick a mass, and then you go left, right. That's the uncertainty that we currently have in the central density of that object. And then you can call out things. So at this density scale, we might have chiral effective field theory that we were talking about, or other nuclear experiments, but those can only go up to so high density, they're not going to get you all the way. We also talked a little bit about PQCT. Those calculations are typically done at much, much higher density. Maybe you might believe you can extrapolate them down here. Even if you believe that, you see that there's a big hole in this density range. You don't have any good probes. Lo and behold, if you look at the masses that correspond to that hole, that's exactly where astrophysical data falls. This is exactly where we get to see these objects. And this would be my bet for what's going to be the next big things. At relatively moderate masses, I think it's going to be the gravitational waves. They're very important. Even with just a handful of additional detections of systems with neutron stars, which is consistent with getting at least one, maybe one more in 04, but 05 with increased sensitivity is going to start in like a year or two. And so getting additional gravitational wave signals down here is totally conceivable, and in the next few years could still very much change the game. We are not yet in large number statistics. At higher densities, due to the way that the tides scale, it's probably going to be other messages, like nicer observations of really massive pulsars can help you up here. Much longer term, if you observe the post-merger signal from from a gravitational wave, so think two neutron stars smash into each other, and then they rattle around in this really complicated fluid motion, that can emit gravitational waves. If you can detect that, you can actually probe densities that are higher than you would ever be able to probe in a stable star. Because this other star is rattling around, it's not stable, it's only supported by sort of the kinetic energy that's in those oscillations. Eventually it will collapse, but in the meantime, you can use that to probe these densities here. And so I think there's a very natural observational plan of how you can work your way up to higher densities that is really still very plausible to be realized over the next few years. So more broadly, there are lots of opportunities and challenges. Don't read every word on the slide. But for example, there's a lot more data that you can think about. So different electromagnetic data, different types of physics inside these stars. Again, they're all imprinted, they're connected to the same equation of states. Next generation detectors, gravitational wave or otherwise. In particular, some of these detectors might be able to break degeneracies that we currently have. Jewel, who's a surf student working with me, is looking at this summer to see if we can help learn more information about distinguishing between GR, ultimately gravity, etc. So there's a lot of cool additional data to think about, the theory behind what you would be able to test. As I mentioned, there are a bunch of applications, cosmology, tests of gravity, how nuclear physics connects to the mass distribution, lots of really interesting physics to do. Challenges are often associated in standard ways. Our big ones are going to be scalable inference and accessibility. These are what I like to highlight. And what I really mean here is that you want to be able to interpret the model that you built. If you make a really big black box and it spits out some answer, how can we be confident that that's the right answer and that we understand what's going on? So doing that in a way that you can still process and connect the theory to all these different observations is a real challenge, and in particular, making it accessible, making it reproducible, something that everyone in the world can understand and then do it for themselves is something I care about a lot. Again, this is why I work on the selection effects for gravitational waves quite a bit. Of course, I've also been talking about just kind of like static fluids, like the stars are just sitting there. There is a much richer world of complex fluids. This is something I've been starting to work on with James and Bart here, using turbulent fluid simulations and then signal processing techniques from gravitational wave literature. You can take this complicated turbulent fluid flow, I'm showing the vorticity of one of the Cartesian components of that, and isolate the important parts of the flow. So if you just ask someone to walk up and say, what's the biggest part of the flow? I think this is doing a decent job of automatically isolating it, and then you can actually go one step further and isolate individual components and structures inside this flow. And once you can do this computationally efficiently, which we now can, as of like last week when I wrote the code to do this, you can then immediately start analyzing the behavior of these structures and try to understand what's going on in the flow, which is otherwise extremely chaotic and turbulent. It's a turbulent flow and difficult to analyze otherwise. And so if you've seen me give a Jamboree talk, you've probably seen this slide before. Again, this is the QR code, so if you want any of the links, you can take a picture of this. This will stay up. These are papers that I have contributed significantly to over the last few years. And so I'm not just listing big collaboration papers with 1,500 authors. These are things that I contributed to significantly myself. It's not with first author. I like to color code it by the different things I think about: nuclear physics, strong gravity, a lot of astrostatistics, detector physics. I'll leave you with this thought. I joined CITA in 2022. These are the papers that have been published since 2022. So I emphasize this to say that the field is still extremely active, extremely productive. There's lots of interesting questions that we can ask with current data, and it's only going to get better over the next few years and in the long run with additional detectors. So thank you very much for your attention. Hopefully I got you at least a little bit excited about neutron stars and what we can say about them now and in the coming years. Thank you again for your attention. I'm happy to take any questions. We'll leave it there.
Thanks, Reed. Covered a lot of ground. Good stuff. I'm sure there's a lot of questions. We don't have a lot of time, but we'll please raise your hands. And if you're on Zoom, please use the raise hand feature, and we'll get to Zoom very soon. Yes, we have a question in the back there.
So, how would this be?
So I'm struggling to hear you.
I'm just wondering, like, how could there, is the material inside like a black hole, like something really theoretical, or is it like really singularity of infinitesimal size?
So I'll repeat the question for the people on Zoom. The question was, do we know what the material inside a black hole is, or is it just a pure singularity? The short answer is no, we don't. So the fact that the material is behind an event horizon means that we can't receive any information and signals from it. So we don't have a great model. There are other, people are working on theories for what might exactly happen there, but we don't have good probes or really a completely self-consistent picture of what's going on. So that's one of the reasons why neutron stars are cool, because we could actually possibly go there and scoop it up if we had a good rocket ship.
Chris Thompson has a question online.
Yes, Chris.
Hi, Reed. Yeah, sorry for not being there. Can you say something about how electromagnetic localizations of neutron star binary mergers, which of course, haven't been happening at a high rate, but will happen at a higher rate in the future, will fold into all of this?
Yeah, so that's a good question. Yeah, I'll repeat the question. So Chris basically asked if you see a binary neutron star merger in gravitational waves, how well can you pinpoint where it came from on the sky? What is the current status of that? And then how that would fold into this. And so it's a very good point, Chris. What limits our ability to localize these neutron star mergers right now is the number of detectors that we have at high sensitivity. We essentially triangulate where they came from, so there's a time delay. The signal's propagating, hits one detector, sometime later hits another detector. It gives you a constraint on the angle. But that really only gives you one angle, and so if you only have two detectors, you get these big sweeping arcs through the sky that can be significant fractions of the entire sky. So as the Virgo detector has come online, this has really helped. We do have some very precisely measured localizations. 17017, the first direct detection of binary neutron stars, is such an example. And so hopefully this happens more and more in the future. I think the point that Chris is trying to drive at is, in addition to these sort of multi-messenger picture that I was stressing, where you can use different observations of different objects, if you can figure out where this neutron star emerged in the sky and point your telescopes at it, you can then also observe multiple messengers from that individual object. The post-merger signal that you expect to see is very rich. There's a lot of physics behind it, and there's a lot of modeling uncertainty in that physics. So in addition to getting better localizations, getting the data in the can for this, we do need to do a better job of modeling that type of explosive environment, which is, again, a very exotic system, to really leverage it to the full ability. But so that's one of the reasons why I didn't stress that in this talk as much, because we do have other probes that are already in the can where we can make progress. But it is something very exciting to look forward to.
Okay, Chris.
I wanted to ask, so if you have a maximum mass arising from the neutron star equation of state, how does that causally create a gap in the mass distribution? It seems as though, it's just a phenomenon that happens where your object collapses to a higher density, becomes a black hole, but why does that then scoop out the number?
Why is it none here? Yeah. So here is the reason that so let me repeat this wrong line. Chris is asking on the slide that I'm showing, we have this dearth, and I sort of attributed this as a possibility to be associated with the maximum mass of a neutron star. And Chris wants to know, is there like some sort of plausible causal mechanism that would connect us? I think that it's not completely implausible for the following reason. As the star collapses in a supernova, we think these things are typically formed through core collapse supernova, the matter gets shoved into a proto-neutron star that's rattling around. And oftentimes there will be continued accretion on top of that while, before the rest of the shock gets blown away. If there is a maximum mass neutron star and you accrete slightly above it, then this reflecting surface that may be launching other shocks or emitting radiation could go away suddenly. And then that would no longer prevent any additional infall. And so it could be that you stop here, right? And that's where you never exceed this maximum mass. You can still always bounce stuff off the surface of the star, or there's a strong neutrino flux or something. But if you get a little bit higher than that and you fall into a black hole, there's no longer anything that's pushing the matter out. So you accrete a lot more and you end up with a larger matter. So I think that that's a physically plausible picture. That being said, sort of the core collapse supernova simulation literature is complicated, and these explosion mechanisms are really complicated, as I'm sure you know. And so even the fact whether the star explodes or not may not necessarily be monotonic. It could be a lot more complicated than that simplistic picture that I painted for you. And it also doesn't have to be that picture that I painted for you, but I do think it's not completely crazy to connect it.
Does the low rate of neutron star mergers keep you up at night?
So one thing that we have, it's becoming increasingly clear, is that the first direct detection of binary neutron stars, 17117, is an increasingly fortuitous event. I was talking with Shantanu on that day. I got out of the shower, someone told me to get online, and then I spent 4 hours in a towel, and then tried to bike to campus and actually biked into a bee, and it got stuck in between my helmet and my face. So a lot of weird things happened that day. And so what I want to stress is that, looking forward, you don't necessarily need these individual golden events where you get every single conceivable messenger to make progress in the field. And so I don't think it's particularly likely that we're going to get a super high SNR pinpoint localization with beautiful kilonova, beautiful other things necessarily right away again, but you don't need that to make progress. And so there's a lot of interesting things, and also I'll mention this, so the large number of new events that are coming in August or October this fall as part of the first chunk of 04, this would be public knowledge, we don't have too many events that are down here, but we do have this guy. Yeah, so we already have something that's really new and interesting around the edge of the gap. We have a lot more events that are sort of piling up right around here. And so if there's this physics that I was talking about, possibly that's sculpting this edge of the gap, I don't think it's unreasonable to think that it could also be affecting this edge of the gap. And we are getting a lot more of information about this. So even if you don't have like the cartoon picture we had in our head of what multi-messenger astrophysics would be happening every single night, there's still a lot new data, a lot of interesting questions. And so I think that that is what the picture we have to have looking forward, rather than just like twiddling our thumbs until, and I twiddle my thumbs sometimes, but we read a lot of papers about interesting things and waiting for those beautiful events.
Okay, we have gone past our normal time. Let me just check. Is there anybody else on Zoom who had a question? Okay, all right. If not, thank you very much, Reed.
I think everyone online, I'm gonna kill the Zoom. Please send questions over email if you have them.
No reservation for 12:45.
Okay, all right, good.
Yes, good. All good?
Yeah.